Okay, higher order equations. To systems. So let's just say we got we'll use the notation of the book. We have this equation. Now, we can easily solve this equation. Yeah.
Wouldn't you have a P of Ty?
Not bad for plagiarists. Okay. Now, okay, yes, P naught of Ty. Okay, I have a bad habit down there. Anyhow, I do that a lot, so watch me. Okay, so we have this. Now, if these are constant coefficients, then this can be pretty easy to solve. If we can factor the characteristic polynomial, because we just make the same assumption we do if we had a second order equation, right? And then the Wronskian, well, we're going to have 3 rows and 3 columns, okay? Because we're going to have a fundamental set with 3 equations, okay? So that can be dealt with, but sometimes it's easier to deal with this as a system of linear equations, okay? But the methods we use in this case are totally analogous to the methods we use for second order equations. So to convert this to a system of differential equations in variables, we let y1 equal y. Now, what we're after is we're after the matrix equation, which when multiplied by y1 up through yn gives us y1 prime up through yn prime, right? Or if it's non-homogeneous, then plus some non-homogeneous part. That's going to involve g of t, and we'll see where that fits in. Okay? So we got y1 equals y. y2 equals y1 prime. y3 equals y2 prime. Okay? And okay, anyhow, seems like I've got too many equations. So our equation here, y triple prime, well, what's y1 prime? y1 prime equals y prime, right? And y3 equals y double prime. Okay? So that y triple prime is y3 prime. Okay? Well, this translates into 3 or 4 equations in these unknowns. Okay? First equation is just, again, well, we've got y1, okay? And when we write this, we're going to replace y by y1, okay? And then we've got this, okay? So again, we'll just remind ourselves that y1 is our y. Then in this equation, this is where we start replacing things, okay? Y triple prime is y3 prime. So there's y triple prime, so we rewrite this equation. That equation becomes y3 prime plus all of this, but we're going to replace y double prime with y2 prime. And
wouldn't you just replace it with y3?
yeah, you'd replace it with y3. Duh. Okay? And y prime is going to replace with y2, and y is going to be replaced with y1. Now, when I do that, I'm going to do everything on this side of the equation because I want y3 prime equal, because that's the way the differential equation is going to come out. Okay? And we don't have to go down to yn, this just goes down to y3. So we got y1, y2, y3. And y1 prime, y2 prime, y3 prime. Okay? So what we then have is, this is equal to negative p2 of t times y double prime being y3, minus p1 of t, y prime being y2, minus p naught of ty, y being y1. Okay? And then plus g of t. So, matrix. Our first row, when we multiply by y1, y2, y3 column vector, we should get y1 prime, right? Well, y1 prime is y2. So what row do we multiply by this column to get y2? Obviously, 0, 1, 0. So this row tells us 0, 1, 0 times this is y2, and the first row is going to give us our y1 prime. So y1 prime equals y2. Second row is 0, 0, 1, which gives us y3 is equal to, well, what's in the second row here? y2 prime. Okay? The third row, okay, y1 is multiplied by negative p naught of t. So we have negative p naught. I don't have room to write the t, but we understand the t. Okay? Negative p naught minus p1, negative p1, after we're not doing a subtraction, and negative p2. And we multiply that by these, and we get this much of this equation. Okay? But y3 prime also has to include g of t. Well, we can't put that into the matrix, and you can play around with it and see why. But if we put it here, then everything works.
It would be negative, right?
No. G of t is positive on this side. Right? It wasn't, the reason these are negative is because these were on the same side as your y3 prime, basically. As your triple derivative.
But if you multiply that back out, you'll get...
You're not multiplying this by anything. In other words, this is y3 prime plus g of t.
Yeah.
And y3 prime is these multiplied by this. y3 prime and I got it wrong, so naturally you're asking about that. Yeah, this needs to be on this side of the equation. Okay?
Or it could just be negative,
so it doesn't
right?
work. I just wrote it down carelessly. So I'm glad you kept me honest. Yeah, to get y1 prime, y2 prime, y3 prime, we have to add 0, 0, G of t to what we get from this matrix multiplication. Now, if I multiply these by these, I get this, and then add this, that puts G of t where it belongs. And then you're into familiar territory, okay? You find your psi matrix, and you'd use variation parameters, okay? Now, whether you can find your psi matrix for given P1, P2, and P3, or P0, P1, and P2, okay? You know, lots of luck. In a real engineering problem in the real world, you're almost certainly going to get something that you can't solve in closed form. Closed form meaning that you can do it in terms of sines and cosines and polynomials and rational functions, and then maybe some special functions, you know, Bessel functions. Yeah. Okay. So you're very likely going to be stuck having to use numerical approximation, which we talked about last time, the Euler method. Okay? And it's a very straightforward method that you need to understand and be able to do by hand for 2- and 3-dimensional systems. Beyond that, it's an exercise in redundancy. And what you need to understand in applying these is something that we might still address in our last week, okay? But you really need a very solid linear algebra to understand that well, which is why I recommend that having had our 2-credit course, which articulated with what the transfer institution wanted at that time, they now kind of want the 3-credit course. So I'm recommending that you take that, because you'll better understand how matrix manipulations can become a little bit unstable and give you false solutions or inaccurate solutions. Okay? So I might talk a little bit about that. I might do a simple example. You know, if your pivots aren't right, they're too small or whatever, you build uncertainties and you accumulate errors. Okay? Right now, if you do the Euler method for 2- and 3-dimensional systems, for systems of 2 and 3 equations, then I know you could do it for any system if you had time. And I know that you would understand how it's programmed and how it works. So I'm not sure we really want to take time to talk about the more subtle aspects of that. But maybe. So anyhow, this is what you've got. If you can solve it, great. If you can't, you've always got approximation methods that you do have to be a little careful with. You also have to understand the intervals on which solutions are viable, which is, you asked me about that at the beginning. It just comes down to, for any point at which all these, for any value of t at which all these are defined, you can get a solution, but it's only good up to asymptotes, okay? So if there's an undefined here and undefined here, your solution can't extend outside of the interval between the two undefined points, or points of discontinuity. That just doesn't have to be undefined, although that's typically what you see. Okay? Make sense?